When you think of lasers, you might imagine science fiction, beams of light cutting through space. But for the US Air Force, lasers are part of real experiments that explore the science of energy conversion and the physics of light. Today, we'll take a closer look at the Air Force laser experiment, where engineers and scientists test directed energy technologies that depend on the same concepts learned in physics class. At White Sands Missile Range in New Mexico, often referred to as WSMR, Air Force researchers are testing directed energy, technologies that use concentrated electromagnetic energy like lasers and high-powered microwaves to affect targets at a distance. Dr. Michael Girgis and Tom Lockhart of the Air Force Research Lab will help us learn about the facility and the experiments happening there.
Directed energy consists of both high-powered microwave and lasers. And the WSMR range is just a phenomenal setup and a location that we want to continue to use just because of the proximity of the equipment that you've got and the capabilities that it brings to directed energy experimentation.
Light is more than just something we see. It's a wave and a particle at the same time. The Air Force laser experiments helps demonstrate both sides of that duality. The laser acts like a wave when it spreads or reflects, but when it transfers energy to a target, it behaves like a stream of photons, carrying individualized packets of light energy.
Yeah, so we have a high-power microwave system and a high-energy laser system. Both came out. We looked at and are exploring the capabilities that both have to offer independently, as well as a joint look in engagement. So your laser engagement is really going to be a thermal energy disposition on the target. So you require the energy to heat up on that target to be able to destroy it. The HPM system gets in through different mechanisms to actually affect the electronics that are flying that system.
So what actually happens when energy hits a target? The laser transfers thermal energy, heating the surface until it melts or burns. And a microwave uses electromagnetic fields to interfere with the target's electronic systems. Each uses a different part of the electromagnetic spectrum, but both depend on the same scientific principles of energy transformation and field interaction. Directed energy systems are perfect examples of energy conversion in action. Electrical energy powers the laser, exciting atoms inside the system until their electrons jump to higher energy levels. When those electrons fall back down, they release energy in the form of light, transforming electricity into electromagnetic energy.
We are looking at the abilities to kind of go after unmanned aerial systems, and it's to hit it with both lasers and high-powered microwave, and seeing the effects of both those. Most of the time we actually hit that and it actually burns a hole, a kinetic effect where it actually drops it out of the sky because of that burned hole.
Lasers and high-powered microwaves both rely on converting energy, but they work in very different ways. Lasers release energy as light photons that heat or burn a target, transferring thermal energy through precise concentrated light. High-powered microwaves, on the other hand, use electromagnetic fields to disrupt electrical systems inside a drone or other device.
With high-powered microwave, it may be a little different. It may just interrupt the actual performance and the weapon system will have to go back to where it came from. It may actually do enough damage that it loses its control, so like an autopilot, and it loses that autopilot and it drops to the ground.
This demonstrates how different parts of the electromagnetic spectrum can be used to deliver energy and how that energy interacts with matter in unique ways. While testing is still ongoing, the Air Force is thinking about how this might impact airmen in the field.
So first off, when you're going to be employing directed energy, it's probably going to be a synergistic look at both DE and kinetic options in the employment. Directed energy offers some unique capabilities of low cost and quick engagement, time of flight. You're looking at time on target immediately based off of photon engagement.
Coming back from Afghanistan last year in October, I was at a base where we had a lot of unmanned systems sitting over and watching everything we do. And so for the future, our airmen would like to not be monitored 24/7. And this will push that back so they don't have that monitoring capability. UASs are being populated everywhere, and we're seeing them all the way from the commercial side to the military application. We've got to understand what they're doing, and we actually got to prevent them from gathering knowledge that they shouldn't have.
The Air Force's experiment also shows how electric and magnetic fields can interact. A laser beam is a traveling electromagnetic wave, a combination of oscillating electric and magnetic fields that move energy through space. White Sands is ideal for this research because it's equipped with sensors and radar systems that can track how these waves move, how energy is transferred, and how materials respond to it.
If you look out, White Sands has got a lot of open space, and we want to make sure we understand the capabilities of directed energy before we actually put it in an urban environment. And this is just an ideal location to do that. It's got a lot of sensing capability. It's got a lot of radar coverage, so we know when stuff goes up, and we can capture that, understand it, bring it back to the research scientists so we can actually look at it from a modeling, simulation, and analysis perspective that we don't have to do numerous tests. We can actually do that with modeling, simulation, and analysis.
This kind of modeling helps scientists predict how energy will behave before conducting more real-world experiments. One of the main goals of this experiment is to see how directed energy can protect airmen from small unmanned aircraft, drones that could pose surveillance or security risks.
So we're looking at exploring the capabilities that directed energy has to offer against counter-UAS, counter unmanned aircraft system threats, small man-portable systems.
By testing these systems, scientists are applying what they know about energy, fields, and light to solve real-world problems safely, efficiently, and sustainably. From electrons jumping between energy levels to photons racing through magnetic fields, the science behind the Air Force laser experiment is a prime example of physics in action, showing energy conversion, waves, and the behavior of light. The next time you study energy or wave interactions, remember, these same concepts power some of the Air Force's most advanced technology and could one day shape your own future in science and engineering.